In the previous video, we walked step by step through how occlusion can be used to create saliency maps. In this video, we are going to apply the method using Python and the Captum package. Specifically, we are going to do this for a model that powers a mini automated car. The saliency maps will show us which pixels are used to direct the car around a track. As we work through this example, you'll see that choosing the best sets of parameters for occlusion is not always that easy. Specifically, you're going to see that sometimes the occlusion patch value can introduce bias. Before we get started, I'd just like to mention that this lesson is part of a wider explainable AI for computer vision course. It's completely free and you can find a link to it in the description. You'll find the article version for this lesson as well as many coding resources. And there is a paid version of the course which I'll talk about at the end of this video. So jumping to the notebook, just a reminder, you can find all of this code in the course page. And in this case, we're working in the occlusion notebook in the permutation folder. So we're going to start with our imports, and we have some standard imports like the PyTorch library. We're going to be downloading our model directly from Hugging Face, and we are going to use the occlusion function from the Captum package. We also have some other imports here in the modeling folder in that Git repo. And yeah, these just allow us to import the model architecture as well as the image dataset used to train the model, or at least the class used to train the model. And that just allows us to format the images correctly when we input them into the model. We'll be working with a model trained on the road following dataset. This dataset is used to train a model that directs an automated car. There is a camera on front of the car, and the model uses the image to make predictions. The predictions are then used to direct the car. Okay, so yeah, as I mentioned, we're going to load our model from Hugging Face. All of the models for the course can be found in this XAI for CV models folder. In this case, we're going to load the car single room model, which is just this CNN trained on images from the single room. So we then use the CNN class to initialize our model architecture. In this case, passing the parameter number of classes equals to 1 just tells the architecture that we're dealing with a continuous target variable or a regression problem. If you remember, we're trying to predict the direction, which is just a continuous value. We then load our state dictionary from that model path from Hugging Face. We move the model to a GPU and set it to evaluation mode. Okay, then kind of similarly, we're just loading the validation images from the validation set for the single room version of this road following dataset. We pass those paths into the image dataset object, and again we just set the number of classes equal to 1 to tell this object that we're dealing with the regression problem. And in total we have 300 validation images. So let's just display one of these for now. We're going to load an example image, move it to the GPU, add a batch dimension, and then just pass that into our model to do a forward pass and get a prediction. And yeah, then we're just going to display that or format that image and display it along with the prediction and the target. You can see the image taken by the automated car and the target direction. The direction is given by coordinates on the x-axis. Lower values, those less than 122, indicate that the car should turn left, and higher values greater than 122 indicate that the car should turn right. In this case, the car should make a gradual right turn. Thankfully, the prediction is not so far off. let's see how occlusion can be used to explain this prediction. Okay, so to do that, we pass the model into the occlusion function to create an occlusion object. We then use this object's attribute function to create a saliency map. And to do that, we pass in our example image, and we have a few parameters here. So the sliding window shapes gives the size of the occlusion patch. And in this case, we have a patch that is 32 by 32 pixels, and setting the first dimension to 3 just means that we will occlude all 3 channels of the image simultaneously. And strides equals to 16 tells us that we will move this occlusion patch by 16 pixels at a time. Okay, so we then format that saliency map as a NumPy array, and you can see when we output the shape, we have 3 by 224 by 224, which is the same dimensions as our input image. Okay, so we do have a saliency map for every channel, but because we occluded all channels simultaneously, each of those saliency maps is going to be the exact same. So we just select the first one, and you can also see that the minimum and maximum values here. So this just tells us that for one of the squares, when we occluded that square, we get, the prediction decreased by 53 points. And similarly, for one of the squares, the prediction increased by 44 points. And you can see these are kind of skewed. And yeah, we just come back to that when we plot the color bar for our saliency map. So yeah, so when plotting the saliency map, what we're going to do is overlay it on top of an edge image. And this just provides a little bit of clarity when interpreting the saliency map. And to do that, we use canny edge detection. So then we just display the image and prediction as we did before. We then display our edge map and overlay a saliency map. And yeah, as I mentioned, to get symmetrical bounds for the saliency map, we just take the absolute or the maximum absolute value and then use those to define the bounds. Otherwise, what will happen is the white values in our saliency map won't correspond to values of 0 saliency. And yeah, then we just create a color bar. And you can see what I mean here, where now we have a symmetrical color bar. The result of all this work is a saliency map that can be interpreted in the unit of the target variable. White locations do not play an important role in the prediction. The very red squares will increase the predicted direction by over 40 points. And similarly, the very blue squares will decrease the predicted direction by over 40 points. Overall, there is more red than blue, which aligns with the overall direction of the car. However, keep in mind that unlike SHAP, occlusion does not have the efficiency property. This means that if you add up all the saliency values, you would not get the original prediction. In other words, the saliency map just shows you how much the prediction would change if you occluded the square, not how much the square has contributed to the prediction. Regardless of the precise interpretation, the saliency map can give us some valuable insight into the model. A key takeaway is that most of the important pixels are on the track. This is good news, as we would expect a robust model not to use background pixels. However, there are still a few background pixels that do not have a saliency of 0. We explore this idea further in a later lesson, where we try to improve the model by training it on images from multiple rooms. For now, we will explore some alternatives to the saliency map that we just generated. So in some cases, you may want to interpret the saliency map in terms of a percentage of maximum saliency. This is particularly true when you're working with probabilities or logits. And to do that, all we do is scale or take the absolutes of the saliency map and then scale it by the absolute maximum. We now only have values between 0 and 1. Using this map, it's clear that the center of the track is the most important region for the prediction. This is because both high, positive, and negative values will have a large percentage. The downside is we do not know in which direction these regions change the prediction. Okay, in some cases, you may also want to create a saliency map for the individual channels or have a different saliency map for each channel. In this case, we just adjust the strides and sliding window parameters so that now the first dimension has a dimension of 1. And you'll notice that this does take longer to run just because we now have to do more forward passes than if we had occluded all the values individually. Looking at the output, this approach typically doesn't produce much insight for standard image problems. It may be able to tell you if one channel is more important than another. You may find more benefit when dealing with multispectral images, like in the previous lesson on permutation feature importance. Okay, so this final adjustment is probably the most important. And if you remember from the theory lesson, I mentioned that the choices you make when doing occlusion can really impact your saliency map. And this includes the strides, the size of the occlusion patch, as well as the occlusion value. And so to show this, we're going to use a different occlusion value, and we're going to use the mean value from the image. So the first thing to do is to calculate the mean value for the image, and then we just pass this into the attribute function using the baselines parameter. And don't confuse this with the baseline prediction that we spoke about in the theory lesson. Looking at the output, you can see that the saliency map is quite different to before. Now, it appears as though the background pixels are the most significant to the model's prediction. This is a worrying result, as we would expect a robust model to only use pixels from the track. Otherwise, when we move to a new room, the car might struggle to make the correct turns. When understanding these results, you need to consider how the occlusion value can introduce bias. In this case, the mean value can be skewed. This is because, as you can see, most of the pixels from the input images are taken up by the track. So the resulting mean may be close to values of the track, and we may end up with a grayish occlusion value. When we occlude the background pixels with this value, they change a lot, leading to a large change in the prediction. However, when we occlude pixels of the track, they don't change that much and don't really affect the prediction. As further evidence, note that the orange bars on the track have become significant. This may be because they are quite different to the mean occlusion value. A similar bias could be introduced using an occlusion value of 0. Ultimately, the problem is that the saliency scores will depend on how far the pixel values are from the occlusion value. One way to get around this is to choose a random value for each channel from the image. We can use that as the occlusion value and simply repeat the same process. In this case, you will need to repeat the process at least 3 times and take an average of the saliency score for each square. This will help reduce some of the variability and bias introduced by any single random occlusion value. As I mentioned, this lesson is part of a wider explainable AI course for computer vision. There, we go into details on methods like occlusion, SHAP, GradCam, integrated gradients, and guided backpropagation. That course is completely free, but there's also a paid version where you'll get access to a course certificate, quizzes, all of the videos ad-free, as well as an ebook which allows you to access the course content offline.